In this video, we're going to use all that we've learned about phasor analysis of circuits in order to solve this standard RLC series circuit. And we're going to do so without solving it by differential equations, which we've seen before. So the first thing you do is you need to convert everything into phasors. So for the voltage source, it's already in terms of cosine. So the phasor version is just going to be 50 angle 30. The resistance, that one doesn't change. It was 25 ohms. It's still going to be 25 ohms. Now for the inductor, the L was 20 millihenries. And we know that for impedance for an inductor, it goes to, call it C here. The impedance of an inductor is j omega L. Now I do want to point out, they didn't actually tell us omega in this problem. They told us the frequency, and omega is the angular frequency. It's 2 pi times f. So we'd have 2 pi times frequency, 60 hertz, times the impedance, 20 millihenries. And if we multiply all this together here, we're going to approximate it with a decimal. So 2 pi times 60 times the 0.02. And we are going to get a 7.54 J. So that is the impedance right there for the inductor. Then we need to convert the capacitor into impedance. And the formula for that, so C is 50 microfarads. And we know that the impedance of a capacitor, you can either write it as 1 over j omega C or negative j over omega C, depending on your preference. I'm going to choose the second one. So again, omega is 2 pi times the frequency is 60. And again, my C is 50 micro. So we're going to have 2 times pi times 60 times 50 micro. Point 0.00005. And then we do the reciprocal of all of that, and we are going to get a negative 53.1 J. So that gives us our impedances here. Notice that since they're all in series, they're going to add together, which means we will get the following here: a combined impedance of 25 for the real part and 7.5 for minus 53.1 for the imaginary part. It's going to be minus 45.56 J. Now, since the overall impedance of the circuit has a negative imaginary part, that means it's a capacitive circuit. They don't ask us that, but just point it out. And we're looking for this current here. So just based on phasor Ohm's law, that means current is going to be the voltage over the impedance here. Now, we need to do this in a calculator. It might be best to first convert it into rectangular. 50 cosine 30 is going to be 43.3, and then 50 sine 30 for the imaginary part is going to be 25J over 25 minus 45.56J. If we divide those, again, you can try to divide them by hand, but much better to use a calculator. We just type all that into the calculator, do our division here. And we get a negative 0.02 plus 0.96J. Then we convert that back into polar form. So that means my phasor I is equal to 0.96 angle 91.2 degrees. So our final answer in terms of time would be I0 of t is 0.96 cosine. Now they wrote omega before, and we can write omega again, or we can actually write out what the omega is we know is 2 pi times 60 t plus 91.2 degrees in amps. Sorry, this is not I0, it's just I. There is no I0 in this problem. So I of t is exactly this current here, and we are able to solve all of this without doing any differential equations, just doing really basic algebra, but unfortunately basic algebra with complex numbers.